Let's start out with a quick introduction to the capacitor and the inductor. So we're going to look at the capacitor and the inductor, and then just see how they behave and use that as a stepping stone to building some intuition for how they impact the voltage calculations that you have in a transmission line. So let's start by reviewing the key equation that governs their behavior. So both of them, they kind of basically act like variable resistors that change over time. And the governing equation in the case of the capacitor is C equals dV dt. And for the inductor, it's V equals to L di dt. And the main general behavior is that this dislikes changes in voltage. So if you try to change the voltage, it fights it. And in the case of the inductor, it doesn't like changes in current. So there's some resistance to changing the voltage or changing the current, and the resistance or the amount that it fights that change is characterized by this C and this L. Now the main bit of intuition that I want you to take away from this going into subsequent discussions is what happens at t equals 0 plus when the voltage first hits the capacitor or the inductor, and what happens at t goes to infinity. So what happens once the capacitor and the inductor has been fully charged. So in the case of the capacitor, it starts out by acting like a short. So it just sucks all the charge that you give it into the plates, and then you end up with a short circuit-like behavior. But then once the capacitor is fully charged, it starts behaving like an open circuit. The inductor basically acts as the opposite. So when it first approaches the inductor at t equals 0 plus, it acts like an open circuit, and then over time it will behave as a short circuit. So if you have the solution for how it behaves as a short circuit, and how the circuit behaves with the capacitor being as an open circuit, you know that it will transition from one solution to the other over time. So the final parameter you need to know is how long, or the shape of the curve of the voltage as it transitions from the solution you have for the short circuit to the open circuit, or in the case of the inductor, the open to the short. And that is defined by the time constant. So tau is going to be equal to RC, or we were also using the letter Z instead for impedance. But you might remember from previous classes that the time constant that defines this evolution and how fast the capacitor charges is defined by the product of RC, and in the case of an inductor, tau is going to be equal to R over L. So in our subsequent discussion, we'll see some examples where we use the fact that we know how it behaves at t equals 0 plus and how it's going to behave at t goes to infinity, and use that to at least intuitively draw out how the capacitor and the inductor make the transmission line circuit behave. And then separately, this time constant will come into effect when we start looking at the actual math setting of the differential equation and solving it.